Welcome back to Ocean 201. We're going to continue our discussion of the history of oceanography with some of the origins of latitude and longitude. In the past, we talked about some historical traditional Polynesian navigation techniques, and now we'll talk some about latitude and longitude since those are what we use today. So some of the earliest recorded systematic European study of the ocean occurred in the Library of Alexandria. And at this library, there were scrolls from ships and land caravans describing their routes, the distances, how long things took. And this was a database that was able to be used by the librarians as sort of, in some respects, very similar to our large oceanographic databases that we have now, where we collect data from ships and satellites, but this was a little less intentional and had a more diverse record of things, I suppose. So the second librarian, Eratosthenes, 200 BC, used these different records from ships and caravans and found out the Earth was round. Not only was it round, he was able to calculate its size. And the way that he could calculate its size was essentially first to recognize that it was in fact round. And the way he did this was he noticed that at the summer solstice, so when the sun is highest in the sky, where he was in Alexandria, a pole that was placed vertically into the ground would cast a small shadow. And he found out that a little bit to the south in Syene, there's no shadow cast by a pole during the solstice. Also, a very deep well at the solstice in Syene, the sun would shine all the way to the bottom of the well, whereas it would not quite make it to the bottom of the well in Alexandria. And so if there's an angle from a pole at the solstice in one location and not in another, then it follows that the Earth has to be round. And not only that, you can use a little bit of trigonometry to then calculate the circumference of the Earth. So by knowing that the distance between the 2 points and by knowing the angle cast by the shadow, you can calculate the circumference. So if the shadow is cast at an angle of about 1/50th of a circle, and you know the distance between these two places, then you can multiply that distance by 50 and come up with the circumference of the Earth. And so the actual circumference of the Earth at the equator is 24,903 miles. It's a little bit shorter around the poles because we're on an oblate spheroid. It's actually a little wider around the around the equator than it is at the poles. And Eratosthenes calculated somewhere between 24,600 miles and 27,967 miles. The reason why we don't know exactly how long his circumference was that he calculated in status, essentially the length of a stadium, and we don't know exactly how long a stadium actually was. So some uncertainty there, but really, really close, which is pretty remarkable. And so if you're on a sphere, you need some system to identify points on a sphere. And so Eratosthenes came up with latitude and longitude system based on landmarks. So latitude are lines parallel to the equator, longitude are lines that go around the poles. And this sort of first attempt at latitude and longitude used different place names to identify different lines of latitude and longitude. For instance, the Alexandria parallel or line of meridian or line of longitude that went through Alexandria. Now, Hipparchus, another librarian, came along afterward and developed the 360-degree system that we know and use today. And so that essentially says that lines of latitude span the equator, and lines of longitude then are divide up the equator and all lines of latitude into 360 degrees. And so for latitude, you have an obvious reference, which is the equator. For longitude, you have no obvious reference, right? There's no start and stop. to these lines of longitude. So originally the reference was Alexandria, where the library was. Eventually it was moved to Greenwich, which is why we have Greenwich Mean Time, or GMT, as a reference point for different time zones. And so a very important thing to know is that the distance between two lines of latitude is constant wherever you are. However, the distance between lines of longitude is not. And that's because as you get to the poles, lines of longitude start to converge, and so the distance between them narrows down to eventually you get to a point and there's no distance between lines of longitude. And so you can calculate that distance as the cosine of latitude, of the degrees of latitude, times your the constant distance between degrees of latitude. The reason why I use a cosine is because the cosine of 0 degrees is 1, and as you get out to 90 degrees, that goes down to 0. And so it essentially just relates the standard distance between lines of latitude to the latitude, the angle you are relative to the equator. And so the degree of latitude is always 60 nautical miles, or around 111 kilometers, whereas the degree of longitude at the equator is the same, but if you go up to, say, 21 degrees south, where we are, is down to 56 nautical miles, or about 103 kilometers. Now, Ptolemy came along afterward in 120 AD. He added minutes and seconds, so finer gradations, to this system of degrees. He also did something else. He recalculated the size of Earth and got it wrong. So his estimate was 30% smaller than Eratosthenes. And this incorrect estimate actually lasted for hundreds of years. So didn't necessarily help people out there. Now, unfortunately, the library was burned in 415 AD. And Hypatia was a librarian at that point. She was actually a noble mathematician and scholar. And this really brought scientific progress to a halt. And in a lot of the world, then people went back to thinking that the Earth was flat again. There was still exploration going on, in large part elsewhere, not in Europe. So the Chinese staged a very large ocean expedition in 1300 AD that went to the Indian and Pacific Oceans, but eventually they turned inward elsewhere. And for quite a while, there was not a good sort of appreciation of the fact that the Earth was round and its actual circumference. Now, one of the issues that you have with latitude and longitude is actually finding your location. So latitude's fairly easy, similar to the star compass. If you know where stars are and the angle that they are relative to the equator, then by measuring the angle of the star relative to where you are, relative to the horizon, you can get a fix. And if you do this in multiple points, or if you do this for multiple stars, then you can essentially triangulate yourself and know where you are relative to the equator. So you know your line of latitude, but you don't know where you are in respect to longitude. And the reason why you don't know is because you can use when the sun rises or sets, or when the sun is directly overhead, to say where you are, but you need to know that relative to where you've been. So essentially, you need to know what time has passed. So if you move lines of longitude, then the time that the sun is directly overhead is going to change. But without an accurate record of time, you can't calculate that, you can't measure it. And so in 1707, there was a giant naval disaster in Sicily where a fleet was sunk and thousands of lives were lost. And after that, British Parliament offered a large reward to anyone who could come up with a way around the longitude problem. And so John Harrison was an English carpenter and clockmaker and developed a chronometer that was able to keep time at sea. Prior to this, most clocks were pendulum clocks, and they don't really work on moving ships. and the spring-wound chronometer is very precise and can run at sea. And so the way this works is essentially the Earth has 360 degrees, and it moves around on its poles in 24 hours. And so if you divide 360 by 24, then you get 15 degrees per hour. So essentially, if you have moved from one point and moved 15 degrees east or west, and you record the time at noon, so when the sun is directly overhead and the shadow is smallest, a shadow cast on the deck of your ship is smallest, and then the next day you've moved 15 degrees and you record the time again that the shadow cast on the deck is smallest, so you're at local noon, then the time that has elapsed will be 24 hours plus or minus 1 hour. So it'll be either 23 hours or 25 hours because you've moved 15 degrees. And so the sun is either going to be overhead earlier or later, depending on what direction you're going. And so, for example, how much later is noon in Hawaii than LA? Well, the longitude of Hawaii is 158 degrees. The longitude of LA is 120 degrees. And so 158 minus 120 is 38 degrees. 38 degrees divided by 15 gives you 2.5 hours. So noon here is about 2.5 hours after noon in LA.